Okay, so let's move on to the final speaker of this session. The topic is rely guarantee reasoning for multi-copy atomic weak memory models. And the speaker is Coughlin, I think.
Yes, thank you.
Yeah.
So, as I'm sure many of you are aware, modern architectures provide fairly weak guarantees considering the execution order of instructions. And this is for a variety of performance reasons. There's lots of low-level optimizations hardware can make. But unfortunately, any semantics that try to reason about this behavior in themselves become quite complex. There's a lot of low-level machine state to track. The behavior is highly non-deterministic due to all the possible reorderings. And they're generally non-compositional in how they define their behavior. You can't combine a series of individual thread behaviors to derive a global behavior. You really have to consider it as a global system right from the get-go. And so naturally, any logics that try to reason about such semantics exhibit the same issues. They're non-compositional in their reasoning, for instance, or perhaps they have to over-approximate to deal with the large amount of non-deterministic behavior. So is there no alternative approach to this coming from a sort of simpler angle? Could we preserve sequentially consistent reasoning so that's your standard notion of concurrency in terms of interleaving, and preserve that into a weak memory context via some side condition? And the benefits here are obvious. You can reuse your existing verification techniques to establish that sequentially consistent judgment. And then you break down the problem from a highly intricate property into two much simpler terms if you can derive a nice division of labor between the two. And so that's what we propose to do with this notion of reordering interference freedom that we're establishing as the side condition. And the idea is that we model the weak memory effects as concurrency within a thread. And then we treat the effects of this concurrency as a form of interference. And then finally, we prove that this interference won't invalidate the reasoning from a sequentially consistent perspective when executed on a weak memory model. And this work is really enabled by a nice program transformation semantics to capture the weak memory effects. It's been validated against a large library of litmus tests for a variety of different architectures, so we're quite confident in its results. And the underlying idea is that these memory models reorder operations. And so it captures the possible weak memory effects and it characterizes a particular weak memory model via this reordering operation, which can be read as alpha reorders before beta becoming alpha prime. And so if you were to execute the snippet beta alpha on a weak memory machine that exhibited this particular reordering, then you could observe behaviors as if you had executed alpha prime beta, just as a simple program transformation. And so to give a more concrete example, ARMv8 exhibits the particular reordering X is assigned Y, can reorder before Y is assigned 6, as long as it executes as X is assigned 6. And so this is store forwarding, if you're familiar with it, where the Y is assigned 6 is being forwarded onto the right to X. And so therefore, if you were to execute the snippet Y is assigned 6, X is assigned Y, you could instead observe the out of order execution of those runs. And so you can embed this notion of reordering within a small step semantics through the addition of a reordering rule, which essentially allows a thread to evaluate certain instructions ahead of time, assuming that that particular instruction can reorder with everything ahead of it in terms of the program order. And this is the only way that weak memory effects actually surface within these semantics. It's all in terms of additional behaviors one thread might decide to evaluate non-deterministically. And so you can effectively view a thread as some sort of a mix between sequential and parallel composition. And we loosely illustrate that here with this graph, with the edges representing dependencies that would actually prevent reordering. And so you expect some of these to be executed in parallel potentially. You could effectively view it as that. But then on top of that, we also have the standard notion of concurrency, but we focus on a notion of multi-copy atomic memory models. And so that includes ARMv8 RISC-V x86 TSO, so quite a broad range of implemented architectures. And the simplifying benefit here is that all threads share a consistent view of shared memory. And so that enables just a standard interleaving semantics with a traditional memory model, memory representation. And so you can just use a standard notion of interleaving to consider how these threads would interact with each other via the shared memory. So that's the semantics. Moving on to the notions of interference. We have our inter-thread interference enabled by that form of just a standard notion of concurrency, as well as intra-thread interference due to the possibility of reordering. Now, because we're building on multi-copy atomic memory models, and we're just using standard interleaving semantics for concurrency, for our inter-thread interference, we can use standard techniques. And so in particular, we decided to build on rely guarantee reasoning to handle that particular case. So as a brief primer, the underlying idea is that from the perspective of each, you analyze each thread independently with their own rely guarantee specification. And so from the perspective of one thread, you assume that all other threads are going to satisfy the rely specification. And then given that assumption, you establish that this thread will satisfy its guarantee relation in terms of how it modifies global state. And you can bolt on pre and post conditions similar to a standard Hoare logic. And so once you establish these judgments over a series of threads, you can compose them to establish a judgment over the concurrent system, given that the guarantee satisfies the relies of the other threads. So if you know the guarantee satisfies the rely of another thread and vice versa, then they shouldn't interfere with each other's reasoning. And so that handles the inter-thread interference. There's still the problem of intra-thread. And so one approach here, for instance, would just to consider all reorderings. But this would be inefficient, similar to considering all interleavings in a concurrent system. So instead, we build on our insight. The reordering relations are generally defined such that they preserve the sequential behavior of a thread. So a thread should not be able to observe the effects of its own reordering. The only way they could actually be observed is via some interaction with its environment. And because we're building on rely guarantee reasoning, we've characterized these interactions, a thread's interactions with its environment, via the rely guarantee specifications. And so if you consider a particular pair of instructions within a thread, if the rely and guarantee specifications for that thread cannot distinguish between the out of order and the in order execution, then no thread in the system can. The thread itself cannot, no thread in the environment can distinguish them. And so it shouldn't affect reasoning. And so we formalized this as a notion of reordering interference freedom, initially for just a pair of instructions. So given a rely and guarantee specification and a pair of reordable instructions, then any property that we can establish over their in-order execution, we ought to be able to establish over their out-of-order execution. Given these conditions, we consider them interference-free, and then we extend this property out to an entire thread by identifying all pairs of reordable instructions within that thread. If you can establish interference freedom for all of those, then you can preserve a traditional rely guarantee judgment over that thread's code as if it executed in order on a sequentially consistent memory model. You can preserve that property onto a weak memory model. And this is a substantial reduction in complexity. Rather than considering all interleavings, we just reduce it down to pairs of interfering instructions. However, there's a bit of an over-approximation here in that if you look at the definition of interference freedom for a pair of instructions, we've quantified over the pre and post condition. And this is beneficial from one light in that you don't have to identify you don't have to track the exact states under which this reordering occurs. And that can be quite difficult to do because there could be a variety of other instructions that can reorder with these at the same time. But you can't express any form of state dependency when establishing interference freedom. And that can be quite limited. So we introduce a notion of a verification condition that's coupled with a particular instruction. And the idea being that whenever that instruction evaluates under whatever reordering that might be, that verification condition should be true. And so under the rely guarantee reasoning of in order rely guarantee reasoning perspective, that's just a proof obligation that has to be demonstrated. And in the interference freedom perspective, that you can leverage those verification conditions to express state dependencies. But it's something of a double-edged sword in that you also have to preserve those verification conditions through reordering. But we find that they're generally trivial enough that this is not a major concern. Another difficulty with the approach is that you have to enumerate all reorderable pairs, and that can be quite tedious due to the amount of, due to the complexity of the weak memory models. But we've automated this away through a data flow analysis, which is fairly easy to implement, as these reordering relations are generally based on a notion of syntactic dependence. And so you can just track the reads and writes of a particular instruction to identify what it can and can't reorder with. This gets a bit harder when you consider address calculations, but you can use an alias analysis to improve results in that context. So to illustrate, we'll consider a simple application, a lock over a shared variable x, the idea being that when the lock is 1, no other threads should modify x or the lock. And so we can encode that in the simple rely. If the lock is 1, then after any environment step, the lock should still be 1, x shouldn't have changed. And so we use the prime variables here to indicate the post state after an environment step. And then applying simple weakest precondition reasoning, we can get back to a precondition of true given the particular post condition we want to establish. And we know that the environment won't invalidate this reasoning because each of those predicates are preserved by that rely. Now this works for the in order case, but the machine might decide to execute some of these things out of order. In particular, the access to X might be evaluated ahead of time as speculative load. And so the data flow analysis would identify the reorderable pair, lock is equal to 1, R is assigned X. The lock is equal to 1 here encodes effectively the exit condition of the while loop. And so given this pair, it's necessary to demonstrate interference freedom between the two of them under this particular rely. Unfortunately, that doesn't hold. It will fail. If you consider the pre and post condition from just before, you can demonstrate that particular judgment over the in order execution, but it will fail under the out of order, trivially because you need to know the lock is equal to 1 prior to the access to X to really be able to say anything after the fact. Fortunately, there's a few ways to resolve this case. So the easiest way is to introduce a memory barrier, which is an instruction at the hardware level that would prevent reordering. Placing this between the access and the loop would prevent the reordering, and therefore the data flow analysis would not consider the demonstration, would not consider the two reorderable, and it wouldn't be required to demonstrate interference freedom. Alternatively, you can modify the specification. And so you could break the relationship between lock and X in the rely condition. And then it's trivial to demonstrate interference freedom. And finally, you could argue that the lock was already 1, and then this loop is somewhat redundant. It's not really establishing any new fact. And so you would achieve that by introducing a verification condition on the while loop's guard, stating that fact. And then you would be able to establish interference freedom, but it would be necessary to demonstrate that that was actually the case via the in-order sequential reasoning for the rely guarantee approach. So to conclude, we've shown how to adapt rely guarantee reasoning from a sequentially consistent perspective onto a weak memory model via a psi condition. And it's entirely standard rely guarantee reasoning in that it supports auxiliary variables, as we demonstrate in the paper. We've also preserved the compositional nature of rely guarantee reasoning. This notion of interference freedom can be established just over one thread. And we've automated away many of the weak memory model specifics through this data flow analysis. The work's been formalized in Isabelle for an abstract memory model, as well as a specific implementation of RMV8. And we're hoping to eventually find some way to support non-multicopy atomic memory models. thank you very much. Happy to answer any questions.
Thank you for the presentation. Are there any questions from the audience? I see that there is a hand raised. So Cliff Jones, feel free to ask the question.
Thanks, I've unmuted. Thanks for a very clear presentation. I always have a trouble with the weak memory examples, that they always look like trick programs that are trying to confuse the reader. Have you looked at applying your techniques to real programs, realistic programs that are trying to achieve a sensible specification, but just happen to use a weak memory implementation?
Yes, so we've applied this in the paper. We applied to Peterson's algorithm, and I'm not sure if you consider that the same algorithm, but it does feature some reordering that's somewhat non-trivial to reason about, and we support that. We have also applied it to sequence lock, if you're familiar with it from the Linux kernel, and it works out there as well. So I think it's useful in realistic cases, yes.
Great. And what time of day is it?
4 a.m., which isn't too bad.
Well done.
Thank you.
Okay, any other questions? I also have a question. Can you, because with rely guarantee reasoning, of course you want to have a compositional approach. Can you comment on how this compares to a monolithic approach, where you're not doing this compositionally?
I'm not too familiar with all of the different approaches that will be non-compositional. We really prefer, at least from the perspective that we're coming from, for a compositional approach, just to how it would scale when reasoning. I imagine you could probably adapt non-compositional approaches if you severely limit the cases you're looking at. Yeah.
Okay. Another question. Yeah, you hint already at support for non-multicopy atomic memory models. So is it hard to add to adapt the technique for another type of weak memory model, for instance?
So as long as it's a multi-copy atomic memory model, this should all work. You just characterize it via a different reordering relation. To adapt to non-multi-copy atomic memory models, it requires significant change, it seems, to the sequentially consistent rely guarantee reasoning sort of side condition. That property, it's hard to adapt that to the non-multi-copy domain. And so we'd have to find some way to modify that. We've explored a few different techniques, while still somehow preserving existing reasoning approaches. And so that's the main limiting factor there. Yeah.
Okay. If there are no further questions, maybe there is still one. Yeah, there is a question. Let's see, Andrew Butterfield.
This is very interesting. I'm just curious about the non-multi-copy. Which processors have that? I'm interested because I'm currently working with an old architecture called Spark. I'm kind of curious.
I suspect Spark is non-multi-copy atomic. The current ones, Power is non-multi-copy atomic. The old version of ARM was supposedly non-multi-copy atomic, but I think you can argue that no one actually implemented that. Yeah, I suspect Spark was non-multi-copy atomic.
Thanks. Yeah, I have to mute the dog is getting excited about your answer. I don't know if you could hear that. Thanks very much for that.
Thank you.
And there is another question. No, that was still Andrew. If there are no further questions, then no. Then thank you again for the talk. Thanks again to all the speakers for the interesting talks. And with this, we wrap up the session. So see you tomorrow, I guess.